Okay. Now we're going to talk about, now we can identify a number of valence electrons. We know how to draw them. We're going to talk about something that is pretty profound in chemistry and really is sort of the underpinning of almost anything that ever happens in a chemical reaction. Maybe not quite everything, but most things. In 1916, two chemists had done enough observations to propose a theory that described not just bonding, like describe the bonding, but describe why the bonding happens. So this is a theory describing why bonding happens. And here's some fundamental observations that go into this theory. First, noble gases are really stable. They don't react. They don't do much of anything. They just hang out there. Right? So they don't react. They also noticed that reactivity depends on the electronic structure, right? Specifically valence electrons. It was also known that things in science, in chemistry, physics, whatever, they always go from high energy to low energy, right? So if something is at a lowest possible energy, then it doesn't do anything. Balls don't roll uphill because downhill is lower energy. So they figured out that something about the noble gases must already be low energy, right? They figured out that the electronic structure of the noble gases must represent a low energy or a stable configuration. So whatever is happening with the arrangement of the electrons must be low energy, must be stable. So if we look at the electron configuration of noble gases, right, they are, actually I think I have them all written out somewhere else. Thought I did, but I don't. So here we go. So for helium, so we'll just do helium, neon, argon, krypton. So I'll do these real quick. Actually, I'm going to pause it and write them out. Okay, so they'll appear in a second. There we go. So here are the noble gas electron configurations. So what is the same about all of them? There's a few things we can note. One is the number of valence electrons, but that kind of omits helium. So I'll come back to helium in a minute, but the number of valence electrons is pretty critical here. So if we look at neon, here's the valence shell. There's 8 valence electrons. Argon, here's the valence shell, shell number 3, 8 valence electrons. Krypton, shell number 4, ignoring the 3Ds, 8 valence electrons, right? So they have 8 valence electrons, and that's what is noteworthy about them. Helium is kind of weird. Helium only has 2 valence electrons, so how is it that helium is super stable also? Well, it turns out that the 8 is important, but it's not important because it's 8. What's important is that if I were to add one more electron to any one of these, helium included, what would I have to do? Hopefully your answer is start a new shell, right? It takes a lot of energy to start a new shell. So what's really going on is the noble gases represent a completely full shell. Or not completely full, but I guess the energy right before you have to start a new shell. So we can summarize this by saying 8 valence electrons. Hydrogen is or helium is an exception with 2, but basically that's it. So this developed the octet rule. The octet rule is based on the idea that noble gases are stable because they have 8 valence electrons, 2 in the case of helium. They have 8 valence electrons, and therefore that is stable. So the octet rule claims that atoms try to attain an outer shell configuration like the noble gases. Usually this is 8 valence electrons, sometimes 2 if they're like helium. But basically, they are trying to be like their nearest noble gas. And this is one of the key underpinnings to understanding anything that happens in chemistry. So you have to understand that elements are trying to get electron configurations like noble gases. 8 electrons in the valence shell, or 2 in the case of helium. There's 2 different ways they can pull this off. One, through covalent bonding, where atoms share. They share electrons. So we're going to talk about that a little bit later in Chapter 5. It's important to know that this happens between two or more nonmetals, right? So two nonmetals. This is because the two elements have to have nearly a full shell. They have to have nearly an octet to work to make this work. So fluorine has 7 valence electrons. It comes up to another fluorine with 7 valence electrons, and what they do is they go, oh, well, let's just share these, and then it looks like, so if these two here in the middle are shared, the red ones are being shared, then it feels to them like they have a full octet, right? There's no, this one's go, oh, I've got all 8 right here, and this one goes, I've got all 8. It doesn't matter to them that they're sharing. That's okay. So we'll talk about that in Chapter 5. In this chapter, we're going to talk mostly about ionic bonding. Ionic bonding is just a little less elegant, a little more just ham-fisted. To get to the number of electrons they need, they just get rid of them, get rid of electrons, or just take them. So, sodium, for example, has 1 valence electrons, and fluorine has 7. Right? Well, they both want an octet, but sodium has so far to go. Sodium would need to gain 7 electrons, because its electron configuration looks like this. 1s2, 2s2, 2p6, 3s1. That's sodium, right? So it would need 7 more electrons to get to be like argon. However, and fluorine's electron configuration looks like this. It's so close. It's so close to having 1. It just needs 1 more electron. It has 7. It just wants that 8th one. Well, it just wants to steal this electron straight from sodium. And sodium actually is kind of okay with it, because while it would take 7 electrons to get all the way up to a noble gas, right? If it just got rid of the 1, it's not like argon, but now it looks like neon, right? It has a full shell now. So this works out great for both of them, and they just trade electrons, or not trade, but one gives up an electron to the other. And so we're going to talk about this in kind of exhaustively in this chapter. So, and that's really all I have to say about the octet rule. I want you to understand that in this chapter, in Chapter 4, where we're going to talk about ionic bonding, and next chapter when we talk about covalent bonding, the driving force, the octet rule, is the same. It's just that they're getting there different ways. But no matter what, atoms are trying to get electron configurations like that of their nearest noble gas.